Okay, today we're going to start looking at separation of variables. Now, an ODE is said to be separable if the derivative, now here it's written in terms of dx on dt, but if that derivative dx on dt can be expressed as a product of a function of x and a function of t. But of course it could be dy on dx or dp on dt or something like that. Essentially, if you can separate it as a product, then you can separate the integrals and then integrate. So here what we do is we would first divide by the function f of x. We would take the dt over to the right hand side, and then now that we've separated it, we can apply the integral on each side and integrate the result so that we have a function of x on the left hand side and a function of t on the right hand side, and therefore find a relationship between x and t. Right? You then later have a little bit more work to do, most likely, because you would like to have x as a function of t if possible. Okay, now let's have a look at an example. For the population equation, all right, so, or logistic equation, so dp on dt is equal to a constant times p plus a. Now recall from last session that we found an equilibrium solution, p subscript eq for equilibrium, at p equals minus a over k when k is non-zero. So that equilibrium we found to be stable if k is negative and unstable if k is positive. Okay, so to find the general solution, we could, since we have this as a product of a function of p and a function of t, the function of t is namely 1. So the function of p here is kp plus a. So we divide by kp plus a. And then we take the dt over to the right hand side and we integrate. Okay, so because I feel like I explain this a little bit better when I write out the details, I'll go ahead and do that on the right hand side here. So I'll take this equation. First thing we do is we take the dt over to the right hand side. So to do that, I'll put a bracket around this. Okay, so we have this. We've separated well, at least the dt, but we have to finish off the separation by dividing both sides by kp plus a. Okay, so I'll go ahead and do that here. I'll move this over, dividing both sides by kp plus a. Okay, so now the separation is complete, and we can apply the integral sign to this. All right, so I'll put in the left-hand side. That's with respect to p. Okay, so that's equal to the integral of 1 with respect to t. Okay, so now that we've got that, we want to complete this integral and do so making some observations here about the form of the left-hand side. Okay, now that proceeds by an integration by substitution. So what we want here is we want to have not a p that we're integrating with respect to, but we want to have an integral with respect to kp plus a. Okay, so you might set out a substitution, let u equal kp plus a. Okay, so let's go ahead and do that. Let u be equal to kp plus a. Okay, and now what I want to do is differentiate u with respect to p so that I can work out how to change my variables. So du on dp is equal to, well, if I just differentiate this, I just have k. Okay, and so now what we can do is use this to show how we're making a substitution of dp. All right, so if you were to temporarily think of this as if it were a fraction, then you would be able to move the dp over to the right hand side. But that's just an aid to memory of the rules of integration. Okay, so what we would have then is du equals k dp, and then I could just divide throughout by k, so that I could have then 1 on k is equal to dp. But what I'm doing is I'm making a substitution, so instead I'll just make this arrow to say that I'm going to replace that. So above this, let's say in aid to memory, okay, because this is not, a real equality there. That's what we would call a differential. Okay, so that's what we want to do in this integral. I want to replace, let's go with the left-hand side here. Okay, so I want to make this substitution, replacing the dp with a du times a 1 on k. So let's introduce the 1 on k there, having made that substitution. And now remember, this over here is just u. Okay, so now that we've made that substitution, we can bring out the 1 on k because that's just a constant, just like this. And now we have, we know the integral of 1 on u. Now this is the exceptional case here because we can write this 1 on u as u to the power of minus 1. Okay, and it's exceptional because if we were to add 1 to the exponent, we would have a 0 exponent, right? So that tells us this one is different, and the actual integral is the logarithm, or the natural logarithm of u. Okay, and now at this point we add a constant of integration, and now we can go ahead and replace the u with what it was, which was kp plus a. All right, now the right-hand side of this integral is very easy because with the integral of 1, it's just t. All right, now since we've already got a constant of integration, we'll leave off that constant of integration, and so we'll say that let's see, this left-hand side here is equal to t. Okay, now I want to rearrange this. Okay, so I'll multiply throughout by k, and so then we'll have log of kp plus a is equal to kc plus kt. And if you want to at this point, you can introduce a new constant of integration, say b, but I won't at this point. Okay, next what I want to do is take this as an exponent in a new equation. So I'll put e to the power of the left-hand side, and then we'll set that equal to e to the power of the right-hand side, which is kt. Okay, so we're getting there at this point. Now, next, what we'll do is we'll use a rule of exponents that we can set out in other words, since in the exponent on the left we have a sum, so that's the same as e to the first thing times e to the second thing. Right? So that's just an exponent law. Okay, now at this point I can say let e to the ck be equal to a, just another constant, and then we're almost there. Now e to the power of the natural logarithm of anything is that inside. Okay, so then this simplifies as kp plus a And then here is our uppercase A, okay, which we can actually put on the right-hand side and divide throughout and call that B. Something like this, right? Okay, so I can simplify this by letting this one be B, and then so we have this, and then we divide throughout, and then let's call 1 on B equal to A. Okay, so we end up with this. Now to finish this off, we can subtract both sides by subtract A from both sides. Okay, so we take A from both sides and then divide both sides by K. Okay, so now we have a function of t. All right, so that's what we've got here on the left of the PDF. Except not quite, because you can see we have a plus or minus, because some people, when they take natural logarithms, they will take the natural log of the absolute value, because you don't want complex values in your as the outcome of taking the logarithm. Okay, so that's the reasons that some people do that. Now, but I can just incorporate that as part of the constant of integration. Okay, and so now at this point, I can introduce saying let this be equal to B and obtain what we have there. P as a function of t is equal to B times e to the kt minus a over k, but that's actually our equilibrium solution that we got earlier, so we can just substitute that in at this point. All right, now I'll save this. And actually we have this on the left. So let's write it that way. Okay, so this gives us our general solution to that population equation or logistic equation. Now, what I want to do at the same time is show you what this looks like when you change the values of K and A. So just run this little diagram here. Okay, so now I'm going to change this constant lowercase a here. Right, now what you see here to start off with is when a is equal to 1 and k is equal to minus 5. So we have exponential decay towards the equilibrium solution that's just a little bit above 0. Or it should be 1/5 or 0.2. Because it's minus a over k. Okay, so we have exponential decay. Now the constants of integration correspond to the particular curves that you're looking at here. Okay, but these other two, lowercase a and lowercase k, they are constants particular to the population equation there. So if I change the lowercase a value, you see that brings up the equilibrium solution higher. Okay. And now let's go back and take that down to 1 again. And let's just manipulate the k value. Now it's currently set at minus 5, so we have exponential decay towards the equilibrium solution. But if I increase this here, you'll see what happens. The equilibrium comes up as I increase this towards 0. Okay, and then suddenly as I cross over 0, you can see what happens. The equilibrium comes up from minus infinite, and we can see that it's now unstable as k becomes positive and goes higher. And again, these are trajectories corresponding to particular initial conditions. Okay, so let's move on to the second example, which says solve the equation y dash is equal to 2xy plus x. Now it is separable, so we'll go through the techniques here. And again, I'm going to write out the details here so I can explain this properly. Okay, so we start with dy on dx is equal to 2xy plus x. Okay, now my first step is to separate this as a product of a function of y and a function of x. So let's factorize the right-hand side here, pulling out an x. So when I factorize, I have 2y plus 1 times x. And the important part here is that I can see that it's separable now, so I can put the function of y with the y and the x with the dx. Okay, so my next step is to display this with the dx on the right-hand side, and then we'll take the 2y plus 1, dividing throughout by that, so I have it with the dy on the left. Okay, so now that we've got that, we have separated it. So next we want to express this as an integral equation. So on the left we have 1 over 2y plus 1, and that's integrating with respect to y. And then on the right-hand side, we have an integral of x with respect to x. Okay, so now we can go ahead and integrate this. So without setting out a u, if you want to, you would say let u equal 2y plus 1, but I really don't have to because I assume you have sufficient experience at this point. So instead, what we'll do to simplify this integral on the left is now I'll just include a 2y plus 1 in here. So 2y plus 1. Okay, now I'm thinking what happens if I were to actually differentiate that. I would generate a 2. So I've got to compensate for that by putting a 1/2 out in front. All right, so that's what we would get here. And so let's just say that this is the same integral. Okay, now let's simplify this, what we have. So we have 1/2 of the logarithm, but it's a natural logarithm of 2y plus 1. Okay, now let's do the the right-hand side. So the right-hand side is the integral of x with respect to x. So we add 1 to the exponent and get 2. But if we were to differentiate x squared, we would bring down the 2. So we need a 1/2. So 1/2 x squared. Hang on. So 1/2 x squared, and now we can include our constant of integration. Okay, so next we might want to multiply throughout by 2. So let's go ahead and do that. Multiply throughout by 2. And then take this as exponents to base e. And when I do that, or you could just rearrange knowing the way this all works. Okay, so we have e to the power of x squared plus 2c. And then we introduce a new constant and say that this is a times e to the x squared. Knowing the rules of exponents. And finally, we want to rearrange this by subtracting 1 from both sides and then dividing by 2. So we can say that y as a function of x is equal to a e to the x squared minus 1, and then divide all of that by 2. So that'll put a minus 1/2 here, and then this will be a new constant, which we could just call a dash, or just call it a, right? You could call that your new a. Okay, so we've now solved this separable ODE. Okay, let's move on to another example. So, logistic equations. An example of a simple endemic model is the logistic equation. I see I have a typo there. Several systems modeled by such an equation include the spread of an infection in a population, the spread of cancer in an organ, adoption of new technologies like mobile phones, for example, or the spread of a rumor. So let's consider the last case, the spread of a rumor, which we could probably all relate to. So it's a good example. Consider the spread of a rumor in more detail. Let rho be the probability that a random person has heard the rumor, and 1 minus rho is the probability that they have not heard it. The rumor spreads at a rate proportional to the product of those two. So we have the ordinary differential equation, or ODE for short, d rho on dt. Now that dash is throwing me off, so I can see I've got another typo in there. So I should probably note that 2 typos on page 18. Okay, d rho on dt is k rho times 1 minus rho. So let's have a look at the figure below, figure 11. On the right of figure 11, we see 2 equilibrium solutions at rho equals 0 and rho equal 1, respectively. Now, this particular curve here is just one of the trajectories that we have. So perhaps I should take this and draw a similar situation. So let's go ahead and do that here. Just put it right under this. Okay, now I'll just take this one. I'll choose a particular k value. Let's just say k is 1 and a is 1. And let's just sketch these trajectories. So what you're seeing here as the black curve is if you started with an initial condition that was between 0 and 1 here, if I fixed k is 1 and a is 1. So that's an example trajectory. So if you did that, trajectories would tend towards the equilibrium 1. Okay, so that's what trajectories would look like there if you started inside between 0 and 1. Now on the left, what we have is a graph of the rate of change d rho on dt with respect to t, showing our 2 equilibrium solutions where d rho on dt is equal to 0. And then we see up here in the middle a maximum rate of change, which occurs somewhere in the middle, but you can view that as corresponding to a maximum slope out here in the middle of the diagram on the right. Okay, so moving on. Let's go ahead and look at how we would solve this equation, this logistic equation for population growth, but it may as well correspond to rumors as well. Okay, so what do we do first? We recognize that this is a separable equation, and then we go ahead and separate it. So first thing we want to do here is take the function of p over to the left-hand side together with the dp. I'll leave the k on the right-hand side to be with the t, or the dt, sorry. Okay, so now we've separated this. And next, we want to apply integral signs. So let's go ahead and do that. So take this, I'll put it on the left, put a 1 there, and then with respect to p. Okay, this is equal to the integral of k with respect to t. Now that integral on the right-hand side is really easy. We just have k t plus c. The left-hand side is a little bit more tricky. So we need a technique called integration by partial fractions, which I'll show you a few more examples in the next week's recordings. So we'll go over integration techniques in more detail next week. Okay, so the technique is to set this out as the sum of two fractions. So we'll say let 1 over this product be equal to 1 over, we're just going to split it up, right? So we'll just split this up first, just like this. Oh, whoops, edit undo. Okay, I'll keep the bracket on it, I reckon. And we want to set out some constants that we seek here. So let's call them alpha and beta, but you can choose your own favorite letters. Let's see, so alpha and beta. Okay, so this is the way it would look like if we were to split this up. Now, we want to think about what happens when we recombine this. If we were to add these two fractions, we would want the same common denominator. So that's our step here, to recombine that. Okay, so let's go ahead and recombine this. We would do so by cross multiplication. So we would multiply this on top and bottom of the left-hand side, and then multiply top and bottom of the second one by p. Okay, so next, now that we have common denominators, we can recombine those, adding the numerators. So I would put numerator plus beta p. Now I can get rid of the second one because we've now recombined it. Okay, so we've assumed then that this should be equal to 1, right? So we see that this is equal to 1. So let's just say we have, okay, and our job is to find the alpha and the beta such that this equation holds true. Okay, now one way to do this would be to expand and collect like terms, right? So that's possibly conceptually the easiest thing to do. So let's go ahead and expand the left-hand side. So we'll expand the alpha into this. Okay, and then we will collect like terms. So let's move this over and factorize the p out of it. Okay, so now that we've done that, so what do we have on the right hand side? We have a single 1 and no p parts of it, right? So what we learn then is that we have to have alpha equal to 1. So let's say we must have alpha equal to 1, and this other one has to be equal to 0. Okay, because there are no p's on the right-hand side of that equation. Right, remember p is a variable, and here presumably alpha, beta, and a are just constants. Okay, so this gives us an easy way to solve for both alpha and beta. We already have alpha. Alpha is clearly equal to 1. But beta has to be equal to alpha over a, or 1 over a. So let's say this gives alpha equals 1 and beta equal to alpha over a, which is just 1 over a. Okay, so now that we have alpha and beta, we can come back to how we separated this up above and say, hence we have this fraction equal to 1 over p plus 1 over a all over 1 minus p over a. Okay, so let's compare with what we have here. Yes, pretty much the same. And so hang on. No, I'm missing something here. I'm missing something. I'm supposed to have alpha over p there. Okay, so I must have made a mistake somewhere in here. So let's see, we recombined, we expanded. I don't know exactly what it was. Okay, but they both have to be 1 over a apparently. Okay, so I'll have a look through that later. So I'll go with what the PDF says. Okay, so essentially now we've separated this. We've got the sum of these two. And now we can pull out the 1 on a and integrate both of those. Now the integral of 1 on p is just log of p, and the integral of 1 over a minus p is minus the integral of 1 over p minus a. And so we just have minus log of p minus a for that part. Okay, now a log rule says that the difference of the logs is the quotient, or the logarithm of the quotient. So we apply that log rule there. And we find that our integral is 1 over a log of p over p minus a. Okay, now comparing with our right-hand side, we have kt plus c, constant of integration times a, is equal to log of p over p minus a. And now again, we take this as an exponent to base e, and we have e to the kt plus ac is e to the log of p over p minus a, but that e to the log, natural log of p over p minus a is just the p over p minus a, so this simplifies considerably. Now we let uppercase A be e to the ac, and we've just about got this done now. Okay, so we want to solve for p as a function of t, so we've got a little bit of algebra to do here. So we want to multiply both sides by p minus a. Okay, so we do that, multiply both sides by p minus a. Next, you want to expand this left-hand side here. So we can expand the left-hand side and collect like terms in terms of p. Okay, so expanding, take the p over to the left-hand side and then factorize. So we end up with uppercase a times kt minus 1 all outside of p minus lowercase a times uppercase a times e to the kt equals 0. Okay, so finally we want to take this a, uppercase a, k to the e to the kt over the right-hand side and then divide by ae to the kt minus 1, which gives us our function of t. Okay, so you could do one more step if you wanted to. You could express, so we'll say dot 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 over here. Okay, I'll rewrite this. We have a, uppercase a, e to the k t, and then we have that over e to the kt minus 1, and so we found that p of t is equal to this. Okay, but what I can do here is divide numerator and denominator by e to the kt, or even a e to the kt. So what we get then is dividing top and bottom by that, we end up with a minus exponent there and a new constant, say b. So this is another way to look at that same equation. Okay, so as t goes to infinite here, this part tends to 0, so you have just a constant on the denominator, so we tend to an equilibrium solution, lowercase a over 1 minus b. Alrighty, and so yes, our in terms of our rumor, we would end up with a sort of particular equilibrium solution there. Okay, let's move on to Newton's law of cooling now. which is another very similar example. And also we have an equation that looks just like the one we solved, or indeed very similar. Okay, so let's go ahead and look at solving Newton's law of cooling. So an example here is if you had, if you go and you're in a hurry, you go to fill some instant coffee in your cup, you put in some cool water, and you put it in the microwave. You press a preset button for say 3 minutes, you walk away, you get distracted by the television, and then you come back after some time to find your coffee boiling, right? I've been in this situation in a hurry at times and done exactly that. So it's basically undrinkable at boiling. So you want to wait a little bit. So you might want to wait until it's 70 degrees Celsius. The temperature in your kitchen, let's suppose it's 25 degrees Celsius. So after 10 seconds, let's suppose that the coffee has cooled to 95. So the question here is how long must you wait to drink the coffee? Okay, so we have what we would call an initial value problem, or IVP for short. We have our differential equation, and then we have t of 0 equals 100. I can see another typo there on page 21. So t of 0 equals 100, and t of 10 is equal to 95. Or let's see, 10 seconds later we have 95. Okay, so this is a separable equation. We see that t equals 25 as a stable equilibrium solution. So we would expect if we left our coffee out for an infinite amount of time and the ambient temperature stayed at 25, we would expect that the cup of coffee would tend towards 25 degrees. Okay, but we're not going to wait an infinite amount of time to drink our coffee, are we? Okay, so this equation is separable. So the first thing we want to do is separate it, divide both sides by t minus 25, apply the integral signs, and then go ahead and integrate. All right, so integrating on the left, we have the natural logarithm of t minus 25, and on the right-hand side, we just have minus kt plus a constant of integration. Okay, so by now we just know how this works out. So we're going to get t is equal to 25 plus some constant times e to the minus kt. Okay, so now we want to use our initial value. T of 0 is 100. And so we sub in t is 0 for time is 0. So we get e to the power of 0 is 1. So on the right-hand side, that just gives us 25 plus a is equal to 100. Okay, now we can solve for a at this point, which is what we want to do. We want to find our particular curve. So subtracting 25 from both sides, we've got 100 minus 25 is 75. So that gives us our value of a, which is 75. So we see now that t is equal to 25 plus 75 e to the minus kt. And that's the solution to our initial value problem. But what we want to know is how long do we have to wait until the coffee has cooled down to 70? Okay, so we have this other condition, t of 10 is equal to 95. Okay, so let's go ahead and sub in the 10 so we can find out that constant that's particular to the coffee. Right? Every material, say aluminium, iron, wood, they all have a particular rate of cooling that's dependent on that material. So my mother told me you want to cook with an iron pan because it tends to hold its temperature, right? That's a quality particular to the iron. All right, so we need to find the K value for coffee, or for the system of the cup of coffee. So that's why we use this t of 10 is 95, right? So we take a measurement first. Okay, so we're subbing in our 10 seconds into the initial value problem solution that we got so that we can solve for k. Okay, so we sub that in, we take the 25 over to the left-hand side and get 95 minus 25 is it 70? Yes, okay. We then divide both sides of the resulting equation by 75, so we get 70 over 75 is equal to e to the power of minus 10k. Okay, then we take natural logarithms. Now that ratio I just talked about, 70 over 75, is the same as 14 over 15. So there's simplified. And then we want to divide by the minus 10. Okay, so we have k is equal to minus 1/10 natural logarithm of 14 over 15. Okay, now a log rule says that we can invert that fraction by taking the minus 1 in, and it becomes an exponent of the 14 over 15, just by a log rule. If you need to review your log rules, go ahead and review your log rules. In fact, I keep a lookup book here in case I forget my log rules. So I'll just go ahead and find those for you. Let's see where that is. Logarithms, okay. So the log rules are here in this little box, so if you need to screenshot that, go ahead. So the log rule of interest here is this third one on the left. Is it? No, it's, where is it? No, it's the second one on the right. Okay, so that n, in this case, is minus 1. I can pull that up and have it be an exponent. Okay, so that's what we're doing there with the n equal to minus 1. We're pulling that up into the exponent, which allows us to invert the fraction. Okay, so we have the natural logarithm of 15 over 14, and then we divide that by 10, and we get that k is equal to 0.0069. Okay, so that gives us our exact equation there, or what I mean is the constant of the cup of coffee, so that we can apply this here and model the rate at which that cup of coffee cools down to 70 degrees Celsius. Okay, so now we want to know, when is it 70? Okay, so we sub 70 into this equation that we got, and we solve for t. So we take the 25 over to the left, and we obtain, let's see, what is that? Is it 45? Okay, so we get 45. We divide throughout by 75, so we have 45 over 75, which I think is 3/5. We divide by our new k that we found, which is minus 0.0069. Okay, we apply the logarithm rule, putting the minus sign up inside as an exponent, which allows us to invert. So we have 1 over 0.0069 natural log of 5 over 3, which gives us 74 seconds approximately. So that's how long we should wait in order to drink that cup of coffee. Okay, so let's go back and review a separable equation which doesn't have a unique solution. All right, so this is an initial value problem that does not have a unique solution. Now, if you recall, earlier in the last session I presented the existence and uniqueness solution, the existence and uniqueness theorem, which says essentially that not every initial value problem has a unique solution, right? Some may have multiple, some may not have any, in a region near that initial solution. Okay, so let's have a look at this example. It's separable. Consider the initial value problem y dash is equal to t times y to the power of 1/3, where when t is equal to 0, y is equal to 0. Okay, so let's separate this by putting the y's with the y's and the t's with the t's. Okay, so we've got that here. We've applied the integration. Now let's integrate. So we add 1 to the exponent of minus 1/3, and we have 2/3. Okay, but if we were to differentiate y to the 2/3, we would bring that 2/3 down. So that's why we need the multiplicative inverse of 2/3 out in front when we integrate this. Okay, so the integral of y to the minus 1/3 is 3/2 y to the 2/3. And the integral of t that we have on the left is just 1/2 t squared, and now we need a constant of integration. Okay, so we would multiply throughout by 2/3 to cancel that 3/2 and attempt to solve for y as a function of t. So we get y to the power of 2/3 is 1/3 t squared plus c. Now let's use our initial condition y of 0 is 0. So we sub in 0 on the left hand side and 0 on the right hand side. So that would give us c is equal to 0. Okay, so far we've got y to the power of 2/3 is 1/3 t squared. Now taking square roots would give us y is equal to plus or minus 1 on root 3 t cubed. And then, so we're taking square roots and then we're cubing both sides. So that's why we get a t to the power of 3 there. Okay, but we need a plus or minus there. So we see that that's not exactly unique, is it? So note that y equals 0 is a solution since it satisfies the original ODE up here. And the initial condition also. So we have y equals 0 as a solution to the initial value problem. And we have this as a solution to the initial value problem. So a solution exists around the initial value y of 0 is 0, but it's not unique. Okay, now according to the existence and uniqueness theorem, this could have been foretold since we, if we set f of ty equal to the right-hand side of this ODE and take partial derivatives, the partial derivative of f with respect to y is t over 3y to the 2/3, which has a discontinuity at the point 0, 0, or our initial condition. All right, and so the theorem requires us to have continuity near that initial condition or initial value. So we see that it does not give us, the theorem does not give us a unique solution near that. So we have multiple solutions in this case. So you've got to take a little bit of care when you're solving even the most simple initial value problems. Okay.